In this video, we're going to talk about the inverse of a matrix. Let's start with the definition. We'll say that a square matrix A is invertible if there exists another matrix, which we'll write A to the negative 1, which is the same size as A, so that A times A to the negative 1 equals I, and A to the negative 1 times A equals I. This matrix, which we've been writing A to the negative 1, is called the inverse of A, or sometimes we just call it A inverse. So for our first example, suppose we're given this matrix A, and we want to check that A inverse is equal to the following matrix. So to do that, we want to multiply A times A inverse, and we want to just confirm that we get the identity matrix. So let's do our usual sort of matrix multiplication. We'll take our matrix A, multiply it by A inverse in the usual way, and sure enough, yeah, we do get this matrix 1, 0, 0, 1, which we could rephrase as the identity matrix. So this is the property that we're looking for, that A times A inverse equals the identity matrix. So that confirms that this matrix here really is the inverse of A. So a couple of comments about this. Not every square matrix is invertible. So if we think about the logic here, an invertible matrix must be square. So invertible implies square, but a square matrix is not necessarily invertible. So square does not imply invertible. A square matrix may or may not be invertible. Second comment that's going to be very useful for us. A times A inverse equals the identity matrix if and only if A inverse times A equals the identity matrix. So when you're confirming that a particular matrix is actually the inverse of A, you only need to check one of these two properties. So you can either check this one or you can check that one, but you don't need to check both, because once you've got one, the other one is guaranteed. So let's look at a couple of formulas. If we have a 2 by 2 matrix A that looks like this, then the determinant of A is written det A, and we calculate it by going AD minus BC. So this probably feels familiar from our discussion on the cross product. Remember, the determinant of a matrix, you just go forwards product minus backwards product. So that's going to be helpful for our main formula here. We're going to look at the formula for the inverse of a 2 by 2 matrix. So to calculate A inverse, we're going to go 1 over determinant of A. Determinant of A is just a number, so you're just getting 1 over determinant of A out in front of this matrix. And then the matrix itself is getting transformed. So we're swapping the diagonal entries, the D and the A swap position, and the off-diagonal entries get their sign changed. So that is the inverse of a 2 by 2 matrix. That will work as long as the determinant of A is non-zero. And if the determinant of A is 0, then the inverse is undefined, or you could say it does not exist. So let's practice our formula for A inverse. The problem is to find A inverse, and we're given the matrix A. So first thing I would do is calculate the determinant of A. We're going to go forwards product minus backwards product. So that's 2 minus a negative 28 gives us a positive 30. And now we can write down our formula for A inverse. So it's going to be 1 over 30 times, and now we're going to modify the matrix A. We're going to swap the entries on the diagonal, and we're going to change the sign on the off diagonal, and that gives us A inverse. So because this is our first time applying that formula, if you wanted to check, you could check that when you multiply A inverse times A, you do actually get the identity matrix. Or alternatively, you could check that if you multiply A times A inverse, you do actually get the identity matrix. Remember that you don't have to check both, because once you know one of these properties, the other one is guaranteed to happen. So typically I'll just check the first one there. Okay, let's try a part B. Let's say our matrix A looks like this. So let's calculate our determinant of A. Forwards product 18 minus the backwards product, which is 18, gives us a determinant of 0. Okay, if the determinant of 0, that means A inverse does not exist. So you can say A inverse is undefined. That's one way to say it. You could say A inverse does not exist. Or yet another way to say it, you could say the original matrix A is not invertible. So let's talk why we care about the inverse of a matrix. So suppose we have a system of equations, and symbolically we'll just write that as AX equals B. If we know that the matrix A inverse exists, what we could do is multiply on the left by A inverse. So we'd have A inverse times AX equals A inverse times B. And what's going to happen on the left side is the A inverse times A are just going to multiply to create the identity matrix. And identity matrix times any matrix or vector just gives us back that original matrix or vector. So we would just get the vector X on the left side. So conceptually what's happening is this is giving us a quick way to solve our system. Because remember, the vector X is just the vector that contains your variables. So if you had two variables, it would be the vector xy, or if you were in R3, it would be the vector xyz. So this is just giving you a quick way to solve for your variables. So let's write this up as a fact. If A inverse exists, then the system of equations, AX equal B, has the unique solution, X equal A inverse times B. So we're actually learning two things here. One, the system has a unique solution. And specifically, what is that unique solution? It's A inverse times B. So let's use A inverse to solve the following system. First thing I would do is just pull out the coefficient matrix. So we'll pull the coefficients out of this, 4, -5, -5, 6. And the idea is now to find the inverse of this coefficient matrix. Okay, so often I'll do this in two steps. First thing, let's think about our determinant. Determinant of A is 24 minus 25. So determinant of A is -1. And then from there, we can write down the inverse of A. So it's going to be 1 over -1. We're going to swap the entries on the diagonal. So the 6 and the 4 change position. And the entries on the off diagonal get their signs changed. Okay, and then the only other adjustment I would make to this is instead of writing 1 over -1, I might just simplify that coefficient and just say negative out in front. Okay, now here comes the key idea from our fact. To solve the system, we're going to use the formula X equal A inverse times B. So we're going to take this inverse matrix that we just built, and we're going to multiply it with B, which are the constants from our original system. So that was -6 and 7. We're going to do our usual matrix multiplication, and we'll have our solution. So we're going to have -36 plus 35 is going to give us -1, and then -30 plus 28 is going to give us -2. This is really the vector 1, 2. So that's our solution vector to our system. If you want, you can leave it written as vector X like that. Or we could just specifically say it's our vector of variables. So xy equals 1, 2. So you can check that that does indeed solve the system, and that process is going to work anytime the matrix A is invertible. So as long as the determinant of A is not 0, this process will work to solve the system. So at this point, we know how to find A inverse for 2x2 matrices, but we should now talk about how to do it for bigger square matrices. So let's say we have a 3x3 matrix. We want to find the inverse of it. What we're going to do is we're going to write down our matrix A, and beside that, we're going to write down the identity matrix of the same size. We're going to go through a sequence of row operations. So this squiggle just represents do some row operations until we produce the identity matrix on the left side. And what will be popping out on the right side is A inverse. So let's talk about why that's guaranteed to happen. Think about the sequence of row operations as being the sequence that undoes A, because we're turning the matrix A into the identity matrix. So as we go through the sequence of operations that undo A, think about what that's going to do to the identity matrix. That's going to build up the matrix that undoes A. And the matrix that undoes A is A inverse. So here's our problem. We're going to find A inverse for the following matrix A. So we're going to start off the process just by writing down the matrix A, and beside that, write down the identity matrix of the same size. So there we go. And then we're going to go through a sequence of row operations to produce the identity matrix on the left side. So first thing we might do here is just a row swap. Let's swap the top two rows. So whatever we do to the left side of the matrix, we need to do to the right side as well. In other words, we're thinking of this entire thing as row 2, and that entire thing comes up to the top. So now we're going to use this 1 as a pivot to clean up the rest of that first column. So we will do row 2 minus 2 row 1, and also row 3 minus 2 row 1. So this will look like 0, 1, negative 3, and then on the right side, continuing to do row 2 minus 2 row 1, 1, negative 2, 0. So if we do a similar kind of thing for the bottom row, it's going to look like 0, negative 2, negative 2, and then on the right side, 0, negative 2, 1. So now we move from our previous pivot down and to the right. We want this guy to be our new pivot for the next step. That's already a 1, so that's going to save us a bit of work. And we're going to eliminate in column 2. So we'll do row 1 minus 2 row 2, and row 3 plus 2 row 2. So let's look at the top row here. Row 1 minus 2 row 2 is going to look like 1, 0, 8, negative 2, 5, 0. And for the bottom row, row 3 plus 2 row 2, 0, 0, negative 8, 2, negative 6, and 1. So now we just need a couple more operations here. We're going to move from our previous pivot down and to the right. This is going to be our new pivot for the third column. So we are going to take row 3 and we're going to divide by negative 8. So that'll give us 0, 0, 1, negative 2 over 8, 6 over 8, and minus 1 over 8. I'm not going to worry about simplifying the fractions until the end. So very last step here, now we're going to use that pivot just to clean up the rest of that third column. So we will do row 1 minus 8 row 3, and also row 2 plus 3 row 3. So let's work on doing row 1 minus 8 row 3. That's going to look like 1, 0, 0, and then things get more interesting over here. So we're going to have negative 2 minus 8 times negative 2 over 8. Okay, so that's like negative 2 plus 2, that's going to be 0. Our next number is going to be 5 minus 8 times 6 over 8. So 5 minus 6 is negative 1. And then last one is a little bit easier. So 0 minus 8 times negative 1 over 8. That's going to be a positive 1. Good. And then let's work on the middle row. Row 2 plus 3 row 3 is going to give us 0, 1, 0. More algebra coming up. So we're going to go 1 plus 3 times negative 2 over 8. I think I'll just think in terms of how many eighths do we have. So 8 over 8 minus 6 over 8 is 2 over 8. Okay, negative 2 plus 3 times 6 over 8 is like negative 16 over 8 plus 18 over 8. So another 2 over 8. And then finally 0 plus 3 times negative 1 over 8 is going to give us negative 3 over 8. And bottom row can just get recopied. So now we've got the identity matrix on the left side, and that tells us that whatever's sitting on the right side here is A inverse. So we could just circle that and we could say that's equal to A inverse. Since there's so many numbers here that are over 8, another possibility is just to pull out the 1 over 8. Then that top row would really read as 0, negative 8 over 8, 8 over 8, and then you just pick out your coefficients from the other two rows. So there we go. We found A inverse for a 3 by 3 matrix. So that same process would work for 4 by 4, 5 by 5, etc. Now, a quick example here to show you what can go wrong with this process. So suppose the problem is to find A inverse for the following 3 by 3 matrix A. So we would start off in the same way as before, where we write down our matrix A, write down the identity matrix beside that, and then we'll just go through some row operations. So this guy would be our pivot here. We would do the operations row 2 minus row 1, and also row 3 minus 2 row 1. And we would produce the following matrix. Then we would move down and to the right. This guy would be our pivot for the next step, and we would think about doing some elimination in that second column. So we do things like row 1 minus row 2, and also row 3 minus row 2. Now, if we just focus on the row 3 minus row 2, that part is interesting because what happens is we get a 0 row on the left side. And once you create a 0 row, no further operations are going to create the identity matrix on the left side. So this is indicating to us that we cannot create the identity matrix on the left side. And what that tells us is that A inverse does not exist. So let's write this up as a fact. If a 0 row appears anywhere on the left side, then A inverse does not exist. And you just stop the process there, done. So now let's talk 3 properties of A inverse. First property, if A inverse exists, then the inverse of A inverse is equal to A. Second property, we're going to look at how the inverse operation interacts with the transpose operation. So the inverse of A transpose is the same thing as the transpose of A inverse. And let's just do a quick example to convince ourselves of that. So let's start with this matrix A here, and let's calculate the left side. So in other words, let's say we want to calculate the inverse of A transpose. So we'd work inside the brackets first. We would transpose our matrix A. So remember, transposing just means turn the rows into columns. So here are the rows of A, put those into the columns. This is now A transpose. And then let's find the inverse of that. So happily, this determinant here is 1. We're just swapping the diagonal entries, changing the sign of the off-diagonal entries. So that's A transpose inverted. And then let's confirm that if we do those operations in the other order, we still get the same matrix. So now we're going to calculate the transpose of A inverse. So now what we're doing on the inside is the inverse operation. So we're taking this matrix A here, calculating its inverse. Okay, so again, the determinant is 1. That makes it particularly nice to write down the inverse. So to get the inverse, we're just going to swap the diagonal entries, change the sign of the off diagonal. So this stuff in the circle now is A inverse, and then we're going to transpose that. So to transpose a matrix, turn the rows into columns. So there we go. This matrix here is the transpose of A inverse. And we're just confirming that when we compare these two matrices, they are the same. Yep, so sure enough, the inverse of A transpose is the same thing as the transpose of A inverse. Third property is probably the most important one. If we have a bunch of matrices multiplied together, and then we want to take the inverse of that product, we can pass the inverse onto the individual matrices, but the order reverses. So it's now AN inverse, next matrix inverse, all the way down to A2 inverse times A1 inverse. So order reverses. What you may want to think about is just a particular case that's going to come up quite often, which is just the situation where you have a couple of matrices multiplied together, and then you take the inverse of that product. So the inverse of AB is B inverse A inverse. We are passing the inverse to the individual matrices, but the order reverses. So let's talk conceptually about why the order reverses. Let's just think about an operation from daily life. Okay, so let's say operation A is you put on your socks in the morning, and operation B is you put on your shoes in the morning. So we do operation A and then operation B. And then, in the evening, when you're undoing this process, you are undoing the individual operations, but you're also reversing the order. So because matrix multiplication represents an action that's being performed, the order has to reverse for the same reason that you have to reverse the order when you're putting on socks and shoes. Okay, now let's look at this property 3 again and imagine that we've just got the same matrix A multiplied by itself a whole bunch of times. Then this property would read as the inverse of A times A times A, etc. is equal to, well, we pass the inverse to the individual matrices and then we reverse the order. So a more concise way to write this would be, say, A to the n, however many times we're multiplying A by itself, A to the n inverse equals A inverse to the n. So that would be a special case of property 3. So quick comment here, since the inverse of A to the n is equal to A inverse raised to the nth power, we can write the symbol A to the negative n without confusion. So it doesn't matter whether you do the inverse first and then raise to the nth power, or whether you raise it to the nth power and then do the inverse, you're getting the same quantity, the same matrix either way. So you can write A to the negative n without worrying about misinterpretation. So here's a matrix A. We're going to find the matrix A to the negative 2. All right, so we can either square this first and then find the inverse, or we can find the inverse, then square that. I would say it's probably easier to do the power first. So that's what I will think about doing here. So we're going to multiply A by itself, and usual matrix multiplication is going to give us 7, 10, 15, and then 22. So now we're going to take the inverse of that. Okay, we might want to think about our determinant before we do that. So determinant of A squared, well, 7 times 22 minus 150. That's going to give us 4. So the inverse of A squared is going to be 1 over 4. Going to change the diagonal, going to swap the diagonal entries and then change the sign of the off diagonal. So you could just leave this as the inverse of A squared, or you could rewrite it and call it A to the negative 2. Or you could write A to the negative 2 is A squared inverted. So another example to help us practice our matrix algebra, we're told that A, B, and X are all invertible matrices and they're all the same size. They're all n by n. We want to solve for the matrix X given this equation. So if I wanted to solve for X, the first thing I would think about doing is just undoing this inverse here. So let's apply the inverse to both sides. We know that the inverse of an inverse just gives us back our original matrix. So we would have AX on the left. And on the right side, we could use the socks and shoes property just to write that as A inverse, B inverse. So we know it was safe to apply the inverse to both sides here because we were told from the equation that we were given that AX is an invertible matrix. Just by seeing the inverse of AX in this formula, we know AX is an invertible matrix, and therefore we know that its inverse is an invertible matrix. Now let's think about how to continue from there. If we want to isolate X, I would think about multiplying by A inverse on the left. So we bring A inverse in on the left, and that means it needs to come in on the left here as well. And we'll try to simplify. So on the left side, A inverse times A is just going to create the identity matrix. And the identity matrix times any matrix just gives us that original matrix. So we're getting X on the left side. On the right side, you could leave your answer as A inverse times B inverse, but it might look slightly better to call that A to the negative 2 B inverse. And there we have solved for X. So I would emphasize it's really important in this problem that A, B, and X are all invertible. In general, if someone gives you a matrix, it's not safe to assume that that matrix is invertible. You would have to be told that it has an inverse in order to think about using the inverse of that matrix. So now we're going to take a look at elementary matrices, and these are matrices that represent row operations. So we're going to go through a short example here. We're just going to ask ourselves the question, how has the identity matrix changed? So for the purpose of this discussion, really helpful to have a picture of the identity matrix in our minds, or maybe just write that up in front of us so that we've got that to look at. And we're going to go through a few different parts here. So let's look at part A. Okay, here we have an elementary matrix. And usually when we're talking about these elementary matrices, we'll call them E1, E2, etc. Elementary matrix E1 just looks like 3, 0, 0, 1. Okay, so let's ask, what was the operation that took us from I to 3, 0, 0, 1? Well, we multiplied the top row by 3. So this elementary matrix, E1, represents that operation of multiplying row 1 by 3. Okay, then we could think about what row operation undoes that. Well, if you want to undo multiplying a row by 3, you would have to divide a row by 3. So you could say this is 1/3 row 1. That's going to undo that. And therefore you can figure out E1 inverse, because E1 inverse is just the matrix that undoes whatever matrix E1 did. So E1 inverse is going to be the matrix that encodes the operation, take row 1 and divide it by 3. And you're always asking yourself, how is the identity matrix changing? So you're just always starting with the identity matrix and you're saying, okay, let's say I perform this operation, row 1 over 3 on that matrix. What would I have? I'd have 1/3, 0, 0, 1. So this matrix here encodes the operation, row 1 over 3. So we're going to go through a few examples like this. We're focusing on figuring out what row operation is being represented by a matrix. We're thinking about what row operation undoes that row operation. And then we're thinking about moving from that row operation to an elementary matrix to get the inverse of our original elementary matrix. So we're going to go through that process for a few different row operations. Okay, next one, let's talk about row swaps. So if someone gives you this elementary matrix E2, which looks like 0, 1, 1, 0, just ask yourself, how has the identity matrix changed? So it might help to have the identity matrix right in front of you. Okay, so what did we do to go from here to here? Well, we swapped rows. So E2 represents swapping row 1 and row 2. Okay, and then we could ask, what row operation undoes a row swap? Well, if you want to undo a row swap, you would just swap those same rows back again. So row 1 swapped with row 2 undoes that operation. Okay, and then E2 inverse is the elementary matrix that encodes undoing that row operation. It's 0, 1, 1, 0. So let's suppose someone gives us this elementary matrix here, which looks like 1, 0, 2, 1. So we would want to imagine the identity matrix, and we would want to ask, how is I changing? So what are we doing to get from I to this? Well, we would have done the row operation where we take row 2 and add 2 times row 1. So the matrix E3 represents doing this row operation. Now, if we wanted to think about E3 inverse, and we wanted a quick way of calculating that, then we would want to say, well, what row operation is going to undo row 2 plus 2 row 1? It would have to be row 2 minus 2 row 1. To undo an addition, we're going to do a subtraction. And the matrix that encodes the undoing is the inverse matrix. So E3 inverse just encodes this operation, row 2 minus 2 row 1. And again, just ask yourself, how is the identity matrix changing? So you start with I, you perform this operation, row 2 minus 2 row 1, and what's happening? You're getting the matrix 1, 0, negative 2, 1. So that's a conceptual way of thinking about E3 inverse. Now, elementary matrices act on the left of a matrix A. So for example, here we have an elementary matrix, and this elementary matrix here encodes the operation taking 2 times row 1. So if we let this elementary matrix act on the matrix A, B, C, D, just multiply the matrices together, you'd have 2A, 2B, C, D. And so sure enough, this elementary matrix multiplies with A and actually performs that row operation. So it's really important that the elementary matrix is sitting on the left of A. You can think about what happens if you did it the other way around. Here's your matrix A. If you tried to put your elementary matrix over here, this is not going to work well. The 2 is actually going to multiply with the stuff in the first column. And so this isn't actually doing a row operation, it's actually doing a column operation. So that's not the correct way to do it. Because we do our Gauss-Jordan process using row operations, we have to have the elementary matrices sitting to the left of our matrix A. So this is the type of problem that we're really trying to solve when it comes to elementary matrices. We're going to do a couple of examples like this just to practice the idea. So someone has given us a matrix A, and we want to write A and A inverse as a product of elementary matrices. All right, so I would start the process just by turning A into the identity matrix using our usual row operations. So let's think about our steps. We would take row 1 and divide it by 2. So 1, 1/2, 0, 1. And then from there, it's just one more step to get the identity matrix. We would use this pivot here just to clean up the second column. So we would go row 1 minus half row 2 to get 1, 0, 0, 1. Okay, so we've created the identity matrix. Now, beside this, we're going to write down the elementary matrix that encodes this row operation. So instead of writing row 1 over 2, we can actually think about the matrix that does that operation. And remember, when you're thinking about elementary matrices, what you always want to ask yourself in every single step is, how is I changing? So if I start off with the matrix I and I do the operation row 1 over 2 on it, I get half 0, 0, 1. So this matrix E1 encodes doing this row operation. Okay, now next step, we're doing a second operation. Now we're doing row 1 minus half row 2. We want another elementary matrix that encodes just that operation. So ignore what happened in the first step. We're just encoding this single row operation. So start with the identity matrix every single time. Start with the identity matrix and just think about what is that going to look like if we do the operation row 1 minus half row 2 on the identity matrix. It would look like 1 minus 1/2, 0, 1. So this matrix E2 encodes doing this operation here. Now the other thing we're going to need to answer the question is the inverse of these matrices. So we're going to need E1 inverse and E2 inverse. Sometimes what people will do is they'll just calculate the inverse, using our formula for a 2 by 2 inverse. And that's fine, but maybe it's a little time consuming. A more conceptual way to do it is to think about how would you reverse the row operation. So if our operation is row 1 over 2, the operation that would reverse that is 2 times row 1. And then think about the matrix that encodes that operation. So take the identity matrix, multiply the top row by 2, it'd be 2, 0, 0, 1. So this is the ideal way of thinking about the inverse of an elementary matrix. Just think about the inverse operation and then encode that in a matrix. All right, let's try the same thing for E2 inverse. So the operation we're talking about is row 1 minus half row 2. The inverse of that would be row 1 plus half row 2. And then think about the matrix that encodes that operation. So you start with the identity matrix, perform the operation row 1 plus half row 2 on it, and it would look like 1, half, 0, 1. Okay, so now we've got all the ingredients that we need to answer the question, and we'll just figure out how to put it all together. So we started with our matrix A. We performed a first row operation, which was represented by E1, and then a second row operation represented by E2, and that produced the identity matrix. Remember that elementary matrices always act on the left of our matrix. So you have E1 just to the left of A, and then you have E2 to the left of that. So if that's true, then this stuff here must be A inverse. because it's a matrix that multiplies with A to give us the identity matrix. So we can say A inverse is E2, E1. Okay, so we've now written A inverse as a product of elementary matrices. And then we could go one step further and we could say, well, A is going to be the inverse of that. So A will be the inverse of E2, E1. According to socks and shoes, that would be E1 inverse, E2 inverse. So as long as you've clearly labeled E1, E2, E1 inverse, E2 inverse earlier in the problem, you can just leave your answer like this. So what elementary matrices really help us do is they help us break a matrix down into the individual row operations that build that matrix. So same type of problem, we've got a matrix A and we want to write A and A inverse as a product of elementary matrices. So let's go through a sequence of row operations just to turn A into the identity matrix. Could think row 1 over 2. And then we could do row 2 minus row 1 just to clean up that first column. Then we could take row 2 and divide it by -1 just to change the sign. And then we could do row 1 minus 2 row 2 just to clean up that second column. And then we've got our identity matrix. Okay, now what we need for each row operation, we need to write down the elementary matrix that encodes that row operation, and we need to write down the elementary matrix that encodes the inverse of that row operation. Whenever you're talking about an elementary matrix, think about the identity matrix. So either have that in your mind or have that on the paper in front of you, and then think, okay, let's perform this operation on the identity matrix. That would give us half 0, 0, 1. Then we need the inverse of that matrix. So you can either just calculate the inverse using our formula, or you can think conceptually. What operation would undo row 1 over 2? Will be multiplying row 1 by 2. And then think about applying that operation to the identity matrix. That gives you your E1 inverse. So we're going to try that process for each of our steps. Okay, next operation is going row 2 minus row 1. We're going to call this matrix E2, and we're going to call its inverse E2 inverse. Okay, so start with the identity matrix. Just highlight that at the top here, and perform row 2 minus row 1 on that matrix. So you'd have something that looks like that. And then inverse of that matrix is going to be represented by row 2 plus row 1. So to undo a subtraction, you're just turning it into an addition. So again, start with your identity matrix and perform the operation row 2 plus row 1 on that. Your bottom row now looks like 1, 1. Next row operation, row 2 over -1. In other words, that's just a sign change in the bottom row. So we'll call our matrix E3, and the inverse of that will be E3 inverse. All right, so start with the identity matrix, do a sign change in the bottom row. That would look like that. And to undo that, we would have to do another sign change in row 2. So I'm just going to write in words sign change in row 2. You can either think of that as minus row 2, or you can think of it as row 2 over -1. Same thing. Either way, it's a sign change. So that elementary matrix is actually going to be the same as E3. So to undo a sign change, you just do another sign change. Okay, so we're acting on the top row of the matrix here. We're taking that top row and going -2 times row 2. So try to keep the identity matrix in your mind. We've got it up at the top of the screen here. If you did row 1 minus 2 row 2 to the identity matrix, you'd have 1, -2, 0, 1. And the operation that's going to undo that is replacing row 1 with row 1 plus 2 row 2. So the way you undo a subtraction is just with an addition. And so that matrix would look like 1, 2, 0, 1. So now our goal is to write A and A inverse as a product of elementary matrices. So let's think conceptually here. We started with A. We performed 4 row operations, and we produced the identity matrix. And we know from our discussion that elementary matrices have to act on the left of A. So the first row operation is represented by E1 coming in and acting on A, and then E2 acted, and then E3 acted, and then E4 acted. So once we have that written down, then we can say, oh, that means all this stuff here, if we think of it as one thing, this stuff here has to be A inverse, because it's something that multiplies with A to give us the identity matrix. So A inverse is E4, E3, E2, E1 in that order. So that's half the question answered right there. We've written A inverse as a product of elementary matrices. And then to get A, we're going to say, well, A is the inverse of A inverse. Using the socks and shoes principle, we need to pass the inverse to each of these matrices, but the order also reverses. So it becomes E1 inverse, E2 inverse, E3 inverse, E4 inverse. And so now we've written A as a product of elementary matrices. So as long as you have your matrices E1 through E4 and E1 inverse through E4 inverse, as long as you've got them clearly labeled earlier in the question, then you would not need to write them down again in the answer. If you didn't work them out before, then you would need to specifically write them down in your answer. A little bit later in the course, in fact, in our next section, we'll see how this concept can be useful in solving systems of equations. So last idea for this section, we're going to look at something called the fundamental theorem of invertible matrices. It says, let A be an n by n matrix. The following statements are equivalent. And then we have 5 statements. A is invertible. The system, AX equal B, has a unique solution for every choice of vector B in Rn. The system AX equal the 0 vector has only the trivial solution. The RREF of matrix A is the identity matrix of the appropriate size, so the n by n identity matrix. And A is a product of elementary matrices. So let's break down what this statement is saying. So first of all, it applies to square matrices, 2 by 2, 3 by 3, etc. And when we say the following statements are equivalent, it means all 5 statements are true or all 5 statements are false. So you could rephrase this entire theorem as, for a given square matrix, all 5 statements are true or all 5 statements are false. So this kind of theorem, which says the following statements are equivalent, is really powerful because it means you're getting 5 pieces of information for the price of 1. So if someone gives you a matrix, you just need to check any one of these statements, and then you automatically know the truth value of all 5 statements. So let's do a couple of quick examples just to illustrate that. So first quick example, let's take the matrix A, which looks like 1, 4, 6, 9. Okay, now let's take a look at these statements here. So statement A is that the matrix is invertible. That's actually pretty quick to check because all we need to do is calculate the determinant of this matrix. So determinant of A is, well, 9 minus 24. In fact, I don't care about the value of it. I just care that it's non-zero. So determinant of A is non-zero. That implies A is invertible. And because statement A is true, that implies all 5 statements are true. So that tells us that any system of the form AX equal B is going to have a unique solution for any choice of B. So as long as this is our coefficient matrix, that system is going to have a unique solution. That forces AX equals 0 to have only the trivial solution. It tells us that if you put this matrix into our REF, you will get the identity matrix. And it also tells us that you can write this matrix as a product of elementary matrices. Now let's do a second quick example. Let's change our matrix A and make it 1, 2, 3, 6. So again, it's pretty easy to check whether this matrix has an inverse or not, because we just need to calculate the determinant of A. So determinant of A is 6 minus 6. In other words, it's 0. And if the determinant is 0, that tells us that A inverse does not exist. So in other words, A is not invertible, doesn't have an inverse. And what that tells us is that all 5 statements are false. Any system that has this matrix as its coefficient matrix does not have a unique solution. So it either has no solution or it has infinitely many solutions. We know that ax equals 0 does not have only the trivial solution. We know that the RREF of this matrix is not the identity matrix. And we know that we can't write A as a product of elementary matrices. So you get all 5 pieces of information just from figuring out any one of the pieces of information. So we've talked about how to find the inverse of a matrix. We've talked about elementary matrices, how to write a matrix as a product of elementary matrices. And we've seen this important fundamental theorem of invertible matrices that helps us figure out a lot of information about square matrices. Thanks for watching.